.25, right on time.
But what is time? Long, long ago, in the very beginning of our planet, which we call Earth, time moved slowly, not by minutes, hours, days, or years, but by units of a million years. Then the first forms of life and a more rapid passage of time, ages each lasting about 100 million years. To the coming of the first living things on Earth, with time measurable in units of 1,000,000 years. To the evolution of man, when the aeons could be divided into years and the years into seasons. The age of Neolithic man. Then man began to travel and learned how to divide the year into seasons, and the seasons into days, and the days into hours, and the hours into minutes and seconds. Time, then, is a measure, a standard measure, devised by man to enable him to keep appointments and to arrive at the right time for catching trains and aeroplanes and all the things we do by the clock. And, as any school child will tell you, the movement of the Earth in its orbit round the sun gives us the spring, summer, autumn, and winter seasons, and the calendar. And the rotation of the Earth on its axis gives us the dawn, the day, the dusk and the night, and the clock. It's all delightfully simple. But once you start going a bit more deeply into this question of time, you soon find it's not nearly so simple as you thought. Time was defined by Sir Isaac Newton, who was born in the 17th century, as something that flowed at a constant rate, unaffected by the motion of material things. But the German metaphysician Immanuel Kant, who was born in the 18th century, was one of the first philosophers who thought that the Newtonian definition was a bit too simple. According to Kant, time does not flow at a constant rate. It depends on what the individual is doing with it. And this is one student who will agree with Kant. He has left himself only 3 minutes to keep an appointment with his girlfriend 1.5 miles away. And although he beats all existing world records for the distance, he will swear that his watch is breaking records too. But this is his lucky day. She hasn't arrived yet. Good. It'll give him time to cool off. Time passes. Does it? Well, very slowly. It's quite impossible to believe that he's only been here half an hour, more like half a century. Time, says Kant, is subjective, and since the next 3 hours will undoubtedly pass in a flash, this is one person who will agree with him. Then we have Einstein, who was born in the 19th century. Einstein's theory of relativity was the biggest upset in preconceived scientific thought since the discovery that the world was round. The Einstein theory is based, as everyone knows, on the idea that time and space cannot be considered separately, that time and space depend on each other. To measure the very great distances of the universe, astronomers have already spoken not of miles, but of time, when they said that such and such a star is so many light years away from us. But time on its own, even when you leave out the variations introduced by Einstein and Kant, is a sufficiently complicated subject. So let us disregard the relative and subjective interruption and return to what we might as well call conventional time. Time as it is generally understood. Let's look first of all at the calendar. Calendars in any language will tell you, although you know already, that there are 365 days in the year, except for every 4th year, which is leap year, when there are 366. But you mustn't forget, if you're thinking of making up a calendar for the year 2000, that sometimes at the end of a century, leap year has to be left out. Leap years come into the calendar because the calendar's time is different from sundial time, which is the time taken by the Earth to make one complete revolution on its axis in relation to the sun. And sundial time is different again from mean solar time, which is based on the average length of the day over the whole year. The length of days vary, of course, because the Earth does not travel around the sun in a perfect circle. The next stage in our exploration of time takes you to an observatory. But before we can observe this new variant of time, you will have to wait until it gets dark. Because this is sidereal time, which is measured by a star, you sometimes have to wait also for a night of good visibility. The modern observatory is in the forefront of automation. It is only a matter of pressing the right buttons, and the whole operation is carried out mechanically. The photographic zenith tube gets into the right position for the shot, and the shutter opens of its own accord to show the passing of the selected star across the meridian. Meanwhile, in the nearby control room, computers register the result, which in turn is permanently recorded on punch cards by another computer. It is an interesting thought that if you can understand the language, you can read what you might call the stop-press news of what's happening to the Earth from the position of a star, which is millions of miles away in the heavens. The day measured by a star is approximately 4 minutes shorter than the 24-hour day measured against the sun. So now we add to an already complicated situation by discovering that something rather odd is taking place. Sidereal time star is gaining on mean solar time at the rate of about 2 hours a month. Or, to put it another way, mean solar time has lost a whole day in the course of a year. Yet another variant of time is standard time, which is the time established by custom or by law over different regions and countries. Standard time in different parts of the world is calculated according to their distance from the prime meridian, which runs through Greenwich, near London. A big country like the United States has no fewer than 4 different standard times. New York goes to work according to what is known as Eastern Time, but in Chicago, it's Central Time. Still traveling westward to places like Colorado, it'll be Mountain Time. And further still to the west, in San Francisco, you set your watch by Pacific Time. So obviously, as you get deeper and deeper into this question of what is time, you find as many variations as you would in a collection of clocks. But since we are so accustomed to associate all radical changes in the measurement of time with great scientists, like Galileo, who among other things discovered the use of the pendulum, we are apt to forget that the man who actually changed the time of day was a prosperous London builder. William Willett campaigned tirelessly for many years to persuade the British people and Parliament that there were untold advantages in what we now call daylight saving time. But it was not until 1916, a year after Willett died, that it was introduced as a means of saving precious daylight in the desperate times of the First World War, and has since been adopted by over half the countries in the world. Despite its obvious advantages, daylight saving time has made life extremely complicated for the men and women whose job it is to work out airline schedules. But daylight saving time is only one of several of the complications of time in relation to travel. This jet airliner is on a routine flight from London to New York. The takeoff was punctual, and the landing they're about to make will be on schedule. But although their watches have all kept good time, they're now all wrong. And the passengers realize that as they have been flying from east to west, they've been steadily pursuing the retreating shadow of the previous night. So that in working out his schedule for the flight, the airline official had to consult the World Time Zone Chart and allow for the fact that according to the sun, New York's time would be 5 hours earlier than time in London. In fact, with supersonic flight already here, it will soon be possible to sit down to breakfast when you leave London at 9 o'clock in the morning and finish it in New York even earlier than you started. Or if you really want to give yourself a surprise, you will be able to leave Tokyo Airport at, say, 10 o'clock on a Wednesday morning, and by crossing the international date line, arrive in San Francisco the night before. Even that is not the final complication if you're a persistent world traveler. Whereas most of the time zones differ from their neighbors by plus or minus 1 hour, Persia differs from its neighbor Iraq by only half an hour. On the other hand, Liberia prefers to have a special time all to itself, universal time plus 44 minutes. And in places in the Arctic Circle, like some parts of Greenland, they don't keep any regular time at all. Until the 20th century, all that was needed for keeping time was a reliable clock ticking away the stately seconds. Even for the navigation of ships at sea, a chronometer accurate to 1/3 of a second a day was considered to be as near perfection as necessity demanded. But as travel and communications became faster and faster, the divisions of time to keep pace had to become smaller. Until today, they can be measured not by seconds or even 1/3 of a second, but by 1/1,000,000th. When you look back upon the elegance and the beauty that have illuminated the art of the clockmaker through many centuries, it comes as something of a shock to find that the timekeeper that has reached such an incredible peak of accuracy looks like a cross between a waste disposal incinerator and an enthusiastic amateur's first attempt to install his own air conditioning. The fundamental section of this breakthrough in ultra-scientific timekeeping is the quartz crystal clock, of which the basis is an ordinary crystal of quartz, such as you would easily find in granite or pieces of rock. If the quartz is subjected to electric charges, it will vibrate. When the electric circuit is correctly timed to the natural frequency of the quartz, the result is an accuracy impossible to achieve by any other previously devised means. In 1955, the cesium clock, which measures time by counting the vibrations of atoms, was added to the quartz crystal clock, and it improved the accuracy of the original quartz crystal clock, the scale of plus or minus 1 second in 900 years. It is more accurate as a timekeeper than the Earth itself in its eternal journey round the sun. Science marches forward, keeping the supplies of knowledge ahead of the insatiable demands of civilization. Travel and communications grow faster and faster. As smaller and smaller we decrease the diminishing subdivisions of time. From the infinity of time and space throughout the universe, to the sometimes desperate importance of subjective time to the human being, science has tied time measurement down with the all but perfect regularity of a quartz crystal cesium atomic clock. But what is this? A rocket to the moon? A rocket into space? Perhaps an incredible adventure to another planet. And what of the problems of measuring time in other planets with different orbits? Perhaps one day in your lifetime, an airliner with a pilot and you as a passenger will leave our Earth and take off for the moon or beyond. And the Earth-made timepiece will keep your pilot in tune with Earth time. And yet, what of the time in the next universe? Whatever time this may be, and however it may be measured. Perhaps we are only beginning, rather than ending, the problem of measuring time.